So we wanted to start today kind of by continuing the conversation we had on Monday, talking about kind of the basic concepts of radioactivity. And so the concept that was kind of mentioned in passing at the end was this idea of half-life. Half-life being the amount of time it takes for half of the radioactive material to actually go through its radioactive decay. And so what's really interesting and consistent about half-life is the fact that it is consistent. Different kinds of chemical reactions actually will have different ways of looking at half-life. So for certain reactions, the more stuff that you have, the longer the half-life is, and the half-lives actually get shorter and shorter and shorter as time goes on. In other kinds of chemical reactions, half-lives increase in length as the reaction proceeds because they slow down so much as a result of the fact that there isn't as much reactant around. But radioactive decays actually go through what's called first order decay. And first order decay is consistent. Every half-life is exactly the same length. So it actually doesn't depend on how much stuff there is. It's just a function of the material itself. So if I start with 1 kilogram of substance, 1 half-life later, there will be half of that material, half of the kilogram. When that same 1620 years passes, that 1/2 of a gram per kilogram will turn into a quarter. When that same 1620 years passes, that quarter of a kilogram turns into an eighth. So 1620 years is the half-life of this particular substance. And every time one of those half-lives elapses, we'll see that half of the material has decayed. Doesn't matter how much we started with. As I made mention of before, this is actually really useful to us. Because it is consistent, we can take advantage of radioactive decays to figure out certain things like how old a sample is. Because if I look at a sample of carbon, for example, let's say I look at an example of a human artifact found from who knows what century, I can take the fact that the carbon-14 half-life is 5,720 years, and I can compare the amount of radioactive carbon in the cadaver's body to how much carbon is in us, and make a comparison and give me a rough idea of how old the unearthed substance is. So half-life is used in that kind of technique. It's one of the most common ways used to date artifacts. Most commonly, we use it with carbon because all living things possess carbon, and as they are alive, they are constantly eating and drinking, producing waste. Their carbon supply is always being exchanged, which means that in terms of the radioactive carbon inside of them, it's a consistent amount. So you have radioactive carbon inside you right now, carbon-14. Now, that radioactive carbon has a half-life of 5,720 years, so the chances of it decaying into nitrogen are relatively low. And even if it did, it would happen so infrequently that it really wouldn't make much of a difference to you if it did. But when you die, you stop exchanging carbon. The amount of carbon-14 in your body is now fixed. And as it decays, it isn't getting replaced. So as time passes on, the amount of carbon-14 in your body starts to decrease. We can get a rough idea based upon kind of relative ratios. Here's what a normal person has in terms of carbon-14. Here's what the sample artifact has in it. How close are they? How many half-lives have gone by? Now, we won't get into all of the complex calculations. We'll kind of keep it simple here. If you see calculation problems related to half-life in any of the homework, quiz, or exam materials, you'll be dealing with full numbers of half-lives. So we can kind of use a table like this to get an idea of how much is left of the original sample. So after one half-life, half of the original sample remains. After two half-lives, a quarter of the original sample remains. After 5 half-lives, 1/32 of the original sample remains, and so on. Every time we go through a new half-life, we cut the existing sample in half. So the next thing that we want to get into then is we want to start looking at, we know that samples are going to decay over time. What kinds of radioactive decay are there? And it turns out that there are 3 primary types of radioactive decay. And those radioactive decays are what are known as ionizing radiation. Ionizing radiation has one trait in particular. When ionizing radiation comes in contact with matter, it is going to ionize that matter. And really what that means that radiation is going to remove electrons from that matter. You heard us talk a lot about free radicals in the last chapter. Free radicals are highly reactive species because they contain unpaired electrons. And those unpaired electrons will seek something to pair them up again and form a new compound. In combustion reactions, that can drive a fire because those free radicals will seek out oxygen, they'll seek out other flammable materials, and they will continue the combustion reaction. In radioactive decays, that free radicalization, that ionization that occurs, usually results in the promotion of cell mutations, cell death, or just in some cases, some general lower level kinds of effects. But the ionization is no joke because we know that ionization is going to cause whatever it comes in contact with, your skin, your body tissues, your organs, to suddenly become reactive material when they're not supposed to be. And depending upon the dosage, depending upon the type of radiation, depending upon how many free radicals are made, we have different kinds of effects. So there are 3 primary types of ionizing radiation. There are alpha particles, beta particles, and gamma particles. And so we'll talk about each of these here in turn. Now, there are some reactions that we can see where a lot of these things can occur. What this is showing is kind of all of the different ways that we can have these different radioactive decays. So we'll get into these more here. Alpha decay. Alpha decay is shown one of two ways. We can either show it as an alpha particle with a mass number of 4 and an atomic number of 2. Alpha being the lowercase Greek letter alpha, which that's what that fish symbol means. We can show it this way, or we can show it based on its isotopic form, a substance that has a mass number of 4 and an atomic number of 2, it's helium. The only difference between this helium, the ones that we've talked about before, this one has no electrons. This is ionized. Where we see alpha decays are in isotopes where we have atomic numbers greater than 83. So if you look at the periodic table, you'll see that most of the elements on the periodic table have decimal number mass numbers. And the reason they have decimal number mass numbers is because they have multiple isotopes, and those isotopes are all stable to the point where we can actually measure them and use them. When we get to bismuth, element number 83, bismuth is the last stable element. Once we get past bismuth and we go to polonium and any of the ones after it, all of those elements are radioactive. Even the ones like thorium and uranium, which have decimal mass numbers, those substances, their isotopes are all radioactive. There are no stable forms of thorium, uranium, actinium, Röntgenium, francium, or any of them after bismuth. Bismuth is the last one that is stable. And so the instability in those elements mainly comes from their size. And so alpha decay is a great way for an isotope to shed weight, because it sheds a total mass of 4, shedding 2 protons in the process. Now, alpha particles, because they are so heavy, they tend to be lower in energy, and their energy is relatively easy to block. A simple piece of paper is usually enough to block alpha radiation. Your clothing, your skin, those are enough to block alpha radiation. So where alpha radiation is particularly dangerous to us is if it happens to get inside of our bodies. Because then the tissue barriers inside of you are not nearly as strong as your skin. Beta decay. Now, beta decay has a lot of different forms. They all basically have the same idea. We have some sort of particle with no mass, and it'll either have a positive or negative 1 in its charge. If it has a negative charge, we call that negatron emission. In negatron emission, what we are talking about is an electron basically being ejected from the nucleus. In the process of that electron being ejected from a nucleus, you see a neutron convert itself into a proton. So beta decay mainly comes from an imbalance of protons and neutrons in the nucleus. When we see beta decay, is because we usually either have too many protons or we have too many neutrons. And beta decay seeks to get it back in balance to stabilize that nucleus. So negatron emission, we see this primarily when we have too many neutrons. In the process of the negatron coming out, a neutron turns into proton to try to reshift the balance. Positrons are exactly the opposite of negatrons. So in a positron emission, we have a positive one charge on the beta particle. We see this where we have too many protons in the nucleus. And so this is more or less the opposite process. A proton is going to eject a positive particle and turn into a neutron. Now, as you might expect, this process, because it has no mass number, the particles here are lighter and therefore move faster, have greater energy. So blocking them is not as simple as just putting a piece of paper in front of you or wearing your clothes or having skin. Beta particles, all forms, will penetrate all of those things. It'll penetrate your clothing. It'll penetrate your skin. It'll penetrate pieces of paper. But if we introduce something with moderate density, such as a 1 centimeter thick aluminum sheet, that is enough density to block beta particles. Now, there is a third form of beta decay called electron capture. This one's a lot more rare. In this one, what we see is very similar in effect to positron emission. What happens here is that an unstable nucleus basically grabs an electron out of the electron cloud. And in that process, we turn a proton into a neutron. Like I said, this one is a little bit more rare. The effect is essentially the same, however. Um, and when this occurs, the gain of stability is going to come with a release of excess energy. And that energy is what we would know as the radiation. So electron capture isn't nearly as common, but it does happen. And when it does, we see pretty much the same effects that we do with positron emission. Proton turns into a neutron. We change the balance of the nucleus and make it more stable. So we've talked about alpha decay. We've talked about beta decay. All that's left is the gamma decay. Now, gamma decay is pure energy. So we've got the Greek letter gamma. It has no charge. It has no mass. It is pure electromagnetic radiation. I'm going to double check this term right there. I think the book means photons, not protons. Because if it was a proton emitted, that would change the atomic number. I'll double check and get back to you on that. I think it's a typo on the slide there. At any rate, because there is no mass, there is no charge. This is pure energy. So this is the highest form of radiation that we have. And because of that, it takes considerable density to block it. So gamma rays go completely through your body. As they go through your body, they ionize anything they encounter. If you are wearing normal clothing or even a hazmat suit, aluminum, anything that might block beta passes through all that stuff too. The only thing that can block gamma, you have to have considerable portions of lead. So gamma decay, the closest thing that we can kind of think of that would be even close to energy is an X-ray. Now, gamma rays are actually even more energetic than X-rays. When you think about what you have to do to get an X-ray taken, you gotta get the lead shield on, you gotta, kind of get yourself set up. If you're the radiological tech, you have to go into that little room behind all that concrete to make sure that you're not getting overexposed to the radiation. That's what it takes. So thick blocks of lead, large masses of concrete, that is what it needs. That's what it takes to block gamma radiation. Now, luckily for us, things that emit gamma rays, there aren't many. They're not common. We don't see them very often. When we do have known encounters with things that are radioactive, there are usually precautions that need to be made and are taken. You go to the dentist and have x-rays taken of your teeth. First thing they do, they put that lead vest on you. Second thing they do, they point that x-ray at the thing that they're looking at. It doesn't really go much further than that. And that's kind of what it is. So we've talked about it. Let's just kind of summarize. When it comes to radiation, there are the three types. Alpha particles, they are the largest, they are the least energetic, they're the easiest to slow down and block. You can block them with your skin, you can block them with your clothing. The major danger with them is if you were in some way able to ingest an alpha radiation source. It could be damaging depending upon the dosage and the duration. Because of their size, they would knock around your cells pretty good. Beta particles can penetrate your skin. But if you have materials like aluminum, although a centimeter thick aluminum is not exactly the thinnest material, you're talking about a little bit less than a third of an inch. In the right circumstances, though, you can block it. It wouldn't take too much to do. Because they can penetrate your skin, they do cause damage to your skin if your skin were exposed to them. And again, depending upon the dosage and the duration, you could see cell mutation, you could see cell death in your skin. So low-level radiation dosage to beta particles on your skin kind of looks and feels like a sunburn of some sort, kind of a mid-grade sunburn. But obviously, the longer the duration is, the more issues you would find. Gamma rays have the most damage potential. They can pretty much penetrate anything. Anything that they walk through, they take electrons from. You need significant amounts of lead, significant measures of concrete to block their passage. So just diagram that. You can see that the alpha particles would only go through to a certain point. The beta particles are able to get through your tissues, but they would not penetrate your bones. And gamma is going to go through everything. Keep in mind, anytime any of these things pass through, they're going to be stripping electrons away, reacting with whatever they encounter. And that's why radiation is so dangerous, because of how it interacts with matter. So let's talk about the kinds of things that happen when these radioactive decays occur. So to understand it, we need to do something called a transmutation reaction. A transmutation reaction is a lot like a balanced chemical equation. The only difference is that instead of abiding by the law of conservation of matter, where we're interested in, okay, there were 35 atoms of carbon on this side and 35 atoms of carbon on this side, that's how I know it's balanced. Here we are looking for nuclear. We are looking for nuclear balancing. And we're going to approximate nuclear balancing by looking at the mass number and the atomic number. So what we're looking for is the conservation of mass number. Does the mass number on the reactant side equal the mass number on the product side? We're also going to look at atomic number. Does the atomic number on the reactant side match up with the atomic number on the product side? This is how we'll be able to keep track of what happens when a nuclear decay goes down. And this is what will allow us to predict the results of those decays. So when a decay occurs, what we have are two different nuclei. We have the parent nucleus, that is the one that decays, and we have the daughter nucleus, that is the one that is the result, the product of that decay. So let's take a look at a couple of examples. So here is an example of an alpha decay. In this alpha decay, we see that we start with a mass number of 238 and an atomic number of 92. Atomic number of 92 tells us that we are dealing with uranium, since uranium has an atomic number of 92, has 92 protons in its nucleus. If it undergoes an alpha decay, alpha particle has a mass number of 4 and an atomic number of 2. So the resulting particle would have an atomic number, or excuse me, a mass number equal to 238 minus 4. That's where the 234 comes from. And its atomic number would be equal to 92 minus 2, which is 90. Element number 90 is TH, thorium. So if we see that uranium is undergoing an alpha decay, that's how we can determine that thorium-234 is the result of that alpha decay. In beta decays, so let's say that thorium-234 just undergoes a beta decay after the original uranium went through an alpha. So I started with a mass number of 234 and an atomic number of 90. If it undergoes a beta decay, this would be a negatron emission. I have a mass number of 0 and an atomic number of -1. 234 minus 0 would give me the mass number 234, so that didn't change. 90 minus -1. Well, the negative of a negative is positive. So 90 plus 1 would be 91. 91 is element protactinium, Pa. And what you are seeing here in these first two examples is actually something part of a larger thing. When radioactive materials undergo a series of decays, we call that a radioactive series. And a radioactive series really doesn't end until we get to some kind of a stable nucleus. Usually, in the case of most of these, that stable nucleus is going to be made out of lead. Sometimes it's other stuff, but it's usually lead. So this decay series could go on. It could have 30 different steps in it. We're just seeing the first two. The uranium turns into thorium. The thorium is still radioactive, so it decays and turns into protactinium. Protactinium is still radioactive, so it turns into actinium. The actinium is still radioactive. It undergoes a decay, turns into francium, and we go so on and so on and so on and so on until we get to the point where we end up at a stable nucleus of some kind. And understand, each one of these radioactivities is going to release radiation, going to release energy that is ionizing. That's one of the reasons why in the world of nuclear chemistry, we are so concerned with the idea of spent radioactive fuel. Because if we're using plutonium for a nuclear bomb, products of that nuclear bomb are going to be radioactive. What happens to them? If we use uranium in a nuclear reactor, what happens to the uranium after it's done giving up whatever it gives up? What about the uranium that doesn't react? What happens to it? What kinds of processes does it have to go through to get to something that is stable and safe, that we're confident won't leach out when we bury it into the ground? So all those things are things we have to think about as we're kind of weighing in all of the different aspects for how do we use nuclear materials appropriately and ethically. And that gets into some of the stuff we're going to talk about next week. Well, after break. For gamma decays, usually with gamma decays, we will see one of two things. We're going to see the gamma particle here. Since the gamma particle has no mass and no charge, often we will see that the daughter nucleus is practically the same. Sometimes it is exactly the same. Sometimes we shake off a little particle like this. So if we see a reaction where a neutron gets shaken off or a proton gets shaken off in the process, that's a real good telltale sign that it's gamma decay. Otherwise, we see very similar kinds of tendencies between the parent and the daughter nucleus. Let's do one more example problem, and then I think we will call it a day here. So let's go through this process, and we're going to balance these transmutation reactions and identify which processes we are looking at. So the real key to these is if you do not have all the information, so oftentimes we will give you information without the atomic number, we're going to want to fill in that information. How we fill in that information is since we have the element symbol, we just find that element on the periodic table and fill in its atomic number. So actinium, it's not given to us, but actinium is element number 89. Francium, Fr, is element number 87, so that's its atomic number. The resulting particle, the thing that is missing, I have 222 minus 218. Well, do the math there, that's 4. 89 minus 87 is 2. Mass number 4, atomic number 2. We are talking about an alpha particle. This is alpha K. All right, let's skip to the bottom one. Cobalt. Cobalt is element number 27. Now, the particle that we are given is a neutron. The way that we can tell that it's a subatomic particle, notice that there are no capital letters here. Lowercase n means neutron. Neutrons have a mass of 1 and a charge of 0. So 60 minus 1 is 59. 27 minus 0 is 27. Element number 27 is still cobalt. So in terms of the daughter nucleus, we've identified it. It's cobalt 59. Cobalt 59, by the way, what's missing? Well, we haven't given off any kind of radioactive particle to get this kind of transformation to occur. Something had to have shut loose that neutron. The only thing that could have done that was a gamma ray. This must be gamma. Okay. So cobalt 60, unstable, undergoes gamma decay. Possibility that in Going through that gamma decay, you get a stable isotope as a result. All right, try this one here on your own. No, we don't have too much time, but see if you can put the pieces together here. All right. Trickiest part about this is we've got to find where vanadium and chromium are. Vanadium is element number 23, chromium 24. One thing about nuclear reactions, unless they are ones like fission or fusion, where we've got nuclear power plant kind of stuff going on here, they're always going to be close to each other. So if you find one, look a couple doors to the left, couple doors to the right, you're going to find the other. 47 minus 47 gives me a 0 for the mass number. 23 minus 24 gives me a -1 for the atomic number. So this is a beta decay. More precisely, this is a negatron emission. Okay, so that's really as far as we're going to take it for today. On Friday, we will continue with this. We'll talk about sealed radiation sources. We'll try to get into some of the application phase now that we've talked about some of the nuts and bolts about how the radiation actually works. Have a great day.